Hi, I'm Sabrina Nazzareni, and I will show you how we work on magma water content of Pico Vulcano in the Azore Island from a clinopyroxene perspective. First of all, I want to introduce you my co-author, Valerio Barbarossa, Enric Scubi, Vittorio Zanon, Maurizio Petrelli, and Pico Vulcano in the background. We are at the Azore Island. They are located here in the middle of the Atlantic Ocean, and in particular at Pico Island, which is the youngest among the Azore volcanic islands, and specifically at the Pico Vulcano, which is the central cone in the Pico Island, because this volcano is on its early evolution stage. With this work, we aim to constrain the plunging system of the Pico Vulcano and to unravel the early evolution of the Azore volcanic system. To do this, we used clinopyroxene phenocryst as sensor to estimate magma water content and thermobarometry. In this task diagram, we reported the composition of all the Azore magmas, and these blue dots are the rocks from Pico. As you can see, most of them are basalts. So we selected basalt representing primitive composition by the lateral activity of Pico Vulcano from less than 40 kiloyears to 1718. The clinopyroxene extracted from this basalt were used for different measurement using several techniques from the single crystal X-ray diffraction, electron probe macroanalysis, polarized infrared spectroscopy on oriented single crystal, this one, Mossbauer spectroscopy, laser ablation, ICP-MS, annealing experiment under hydrogen gas flux, and all the data that we measured allow us to have a very detailed crystal chemistry and water content characterization of our clinopyroxene. Our result was recently published in a contribution Mineralogy and Petrology. So coming to the results, we observed in the infrared spectra OH band, typical of augite composition, only on 3 samples. The remaining 4 have very weak to absent OH band, and if we estimate the water content of this clinopyroxene, we go from 0 to 120. This great variability in the OH content of our sample posed us a question if this sample were originally dry or suffered hydrogen loss. To answer this, we performed an annealing experiment at 700 and 800 degrees C for several hours, and here in this infrared spectra you can see how the OH band intensity increased after each annealing experiment. So to answer the question, yes, how clinopyroxene suffered hydrogen loss? Next question is where this hydrogen was lost, in a magma chamber or after the eruption. To answer this new question, we estimate the closure temperature of pyroxene iron magnesium intracrystalline exchange, because this temperature is related to the cooling rates of the clinopyroxene host lava. And as is reported in this plot, there is a correlation, some correlation between the hydrogen, the water content recovered in our clinopyroxene and the closure temperature. So we suggest that the dehydration process occurred in 2 steps. One at high pressure in a magma chamber, and a second one after the eruption by iron redox processes. Next step was to estimate pressure and temperature of crystallization of clinopyroxene And to do this, we use two different approaches, one based on the chemistry of the crystal liquid pairs, and the other one based on the crystal structure of the cyanopyroxene by measuring the octahedral volume and the cell volume of our sample. These two approaches converge to a same result, that is that our pyroxene start to crystallize at 9-8 kilobars up to 4-5 kilobars. If we put together all this data and we put them in a geological model, we can have a new sketch of the volcanological evolution of Pico from a pyroxene perspective. Our cyanopyroxene started crystallized in the lithospheric mantle around 24-27 kilometer and up depth up to the oceanic crust mantle boundary around 12-15 kilometer depth. And after that, the magma probably erupted to the surface. The magma water content recorded by pyroxene in this from the lithosphere to the crust mantle boundary is more or less the same, because it varies at the lithospheric depth from 0.7 to 1.2 weight%, and at the crust mantle boundary from 1 to 1.2 weight%. So we can say that the water content in magma from the lithosphere where pyroxene started crystallization up to the oceanic crust mantle boundary did not change significantly, and was around on average to 1 weight%. So, to conclude, I want to thank the Italian young crystallographer for having organized this very interesting event, and you all.